123麦克风测试，123麦克风测试。麦克风测试，123麦克风测试。
15 还是要在哪里比较
都可以啊，看你啊，会不会比较好？或者说因为我们是从后面那边拍。哦，好，老师，这里，前三，对，老师那边好像有人，有人，对，坐前面，对。
就这是我们不给他们拍，他们可以拿手机这样拍，
是
可是照片，对，他们可以好，就是把照片放在 Android 的基本上面，然后大家可以下载，就是不是独家的，你知道吗？守德老师，
没关系啊，他如果来，他会报。
可以了，他那个包就可以了，可以了，都可以了。哦，OK，来。是，哦，好。
好，坐这里。
对，先坐。哎，可以，给了，在桌上。哎，可以，请拍。
就直接我们都请他全部进来了。
好。
那三位，
会不会有人？
三位什么东西？
会不会有人没来呀、哎，郭汉，哎，谢啦。那你去跟那老师可以差不多。好。哎，老师，快快快，老师，老师，您已经最后一名了，快！哎，等一下，老师等我。可以可以，请。没有，老师您要坐前3排。
Please be seated. Okay, please be seated. Ladies and gentlemen, it's my great honor to introduce the speaker today, Dr. Yann LeCun. Dr. Yann LeCun is the director of AI Research Lab at Facebook, a senior professor of data science, computer science, neuroscience, and EE at NYU. Dr. LeCun received his PhD in computer science from University Paris at Marie Curie in Paris in 1987. And he joined AT&T Bell Lab in Hongdae in 88. He became the head of image processing research department at AT&T Bell Lab in 1996 and joined NYU as a full professor in 2003. He was named the director of AI research at Facebook in 2013. The research interests of Dr. LeCun including AI, machine learning, and computer perception, and so on. Dr. LeCun is well known as the father of CNN. He received numerous awards, including IEEE Neural Net Pioneer Award, and he is also a NAE member. Please join me to welcome Dr. LeCun.
Thank you. Well, thank you for the introduction. It's a pleasure to be here. It's my second time in Taiwan, and I see a number of familiar faces here. I just chatting with Homer Chen here, who we haven't seen each other in 20 years or so. Not only did we used to be colleagues at Bell Labs, we were also neighbors. We lived across the street from each other. So our kids were little when they met. And my new neighbor in New Jersey is also from Taiwan, actually, from Tainan. And my future daughter-in-law is also from Taiwan. So, and my name sounds Chinese. In fact, you can probably write it this way. Okay, so I'm going to talk about deep learning, kind of give you a bit of a status and state of the art, and then talk about the challenges that we're facing to making progress towards AI. If you've seen some of my talks that have been floating around on the internet, this is going to look familiar, but every time I give the talk, when you pass a certain age, you kind of keep saying the same things, except, I change it a little bit every time, so you get the latest version. So I'm sure a lot of you are familiar with machine learning and deep learning, but I'm going to go very quickly on a sort of quick introduction to the basic idea of deep learning. So a lot of deep learning today is based on a paradigm of machine learning called supervised learning, and all of the recent success of practical success of machine learning essentially rely on supervised learning, right? So you want to train a machine to classify cars from airplanes. Your machine is going to be some sort of parameterized function symbolized by those knobs here. And for the cars, when you show an image of a car, you want the machine to turn on the red light. And when you show an image of an airplane, you want it to turn on the green light. And so you show a car and you tune the knobs a little bit so that the green light brightness increases. And then you show an airplane, and if the green light is not on, you tune the knobs a little bit so that the green light brightness increases. And the magic behind machine learning is that, eventually, as you show millions of examples, and the machine settles on the setting of the knobs, so that all cars are classified as cars and all planes are classified as planes. But of course, the first question you have to ask is, what do you put? How do you build this machine with the knobs? So in fact, the first machine of this type actually had knobs. This was the perceptron. It was built in 1957 at Cornell University. And you see Frank Rosenblatt here, the designer of it, on the panel on the right, is holding a module with 8 weights on it. And each weight is a potentiometer with a motor on it. And that's how the system was implemented. It was an analog computer with tunable knobs, essentially, that were kind of tuned automatically. That was the first learning machine. Now we can replace this with 3 lines of Python. But it took a lot of effort to build this. But this kind of founded the model of pattern recognition for many decades afterwards, where the way you do pattern recognition is you take a raw signal, you build a feature extractor, generally by hand, that turns this into a vector of features that can be digested by a simple learning algorithm like a linear classifier, which is what the perceptron was. And that's been the model of pattern recognition for decades. What deep learning did was replace this model, which is the one on the top, by the one at the bottom, where instead of having just one handcrafted module followed by a simple trainable module, you build your machine as a cascade of trainable modules in such a way that each module transforms the data on its input into something a little more abstract, a little more appropriate for the task. And the trick is to train all of those modules together so as to minimize some sort of objective function, perhaps the distance between the answer you want and the answer you get. So now the next question you have to ask, of course, is what do I put in those boxes? And what people have settled on over the last few years is a model of essentially neural networks, kind of a renewed architecture of neural networks, where each module is essentially is either a linear transform, basically a matrix. Okay, so imagine you represent your data as a vector. You multiply this vector by a matrix. And the coefficient in this matrix are the knobs that you can adjust. And then the second type of module, which is a pointwise nonlinearity, which in most modern neural nets is a very simple function, a half-wave rectifier that people in the business call ReLU. That means rectified linear unit. So the ReLU is a lot simpler than the type of nonlinear functions we were using in the 80s and 90s with neural nets that were sigmoids. It has some advantages, one of which is that it's contrast equivariant. In other words, if you multiply all the values of the input by some factor, then the output would be also multiplied by some factor, but otherwise unchanged if you ignore the biases in the system. And that's a desirable property. That means it's kind of the scale of the data doesn't matter. So the learning algorithm changes the weight, and it changes the weight using the backpropagation algorithm. I'm not going to go through the detail of it, probably because all of you know it, but also because it's a very simple practical application of a chain rule. And once you get the idea, it's very simple. Basically, you need to figure out the partial derivatives of whatever cost function you want to minimize, which perhaps measures the discrepancy between the answer you want and the answer you get with respect to all the parameters in the system. It turns out you can do this by applying chain rule, which will propagate the gradients backwards. So you multiply the gradients of the output of a module with the gradient of the cost function with respect to the output of a module by the Jacobian of that module, and you get the gradient with respect to the input of that module. And you can do this from module to module. This has been sort of implemented as a software, a sort of easy software framework. The first time, I think, around 1991, 1992. This was Léon Bottou who had the idea in the late 80s that you could assemble modules regardless of their functionality and then kind of backpropagate gradient automatically as long as the graph of connection was without loops. And if they had loops, you had to kind of unroll them. And he and I implemented a framework at the time called SN, which eventually became an open source software called Lush, which basically implemented this idea of, you can assemble modules and you get automatic differentiation. Now you see this implemented in every deep learning framework that you can download, Torch, PyTorch, TensorFlow, Theano, Keras, all of those, MXNet, all those things, Caffe, they all use the same idea that you assemble modules and you can backpropagate through them. So the next idea, of course, is that multiplying a vector by a matrix is good if your vector is not too large, but if your vector is a whole image, it becomes very expensive, and it's also kind of wasteful. And so the next idea came very early, the idea of convolutional networks. And convolutional networks are just a particular way of constraining the matrices that you use to multiply inputs to produce outputs. In the case of convolutional nets, the matrices implement the convolution operation, which of course, I'm sure many of you are very familiar with, but basically if you have an input image, you take a window out of the image and compute the dot product of the pixels in this window with a bunch of weights. This is called a convolution kernel. And the dot product, you put the result in the corresponding pixel on the output. And then you swipe this window over the entire input and record the results in the output. What you do here is you basically detect a type of feature over the entire image independently of its position. And so this is a very classical operation in image processing. And the trick is that, of course, we're going to learn those filters. So a typical convolutional net will have multiple filters applied to the input, producing multiple feature maps. And then the second stage would be a pooling operation, which consists in aggregating the values within a region here with a max operation or an average or an LP norm, or a log of sum of exponential, something that is independent of the order of the inputs. And the purpose of this operation is to build a little bit of shift invariance or distortion invariance in the representation. And then you repeat the process. So the next layer up, again, performs convolutions, multiple convolutions on the multiple maps, adds up the result, pass the result through a nonlinearity, and then again there is a pooling. And then you repeat the operation multiple times. And the idea was suggested really by neuroscience. So there's classic work in neuroscience from the 60s by Huber and Wiesel, so classical that it's Nobel Prize winning, that studied the visual cortex, and Kuniko Fukushima in Japan in the 1980s came up with the architecture called the neocognitron that basically had this, but it didn't have the backpropagation learning algorithm. So he had to use sort of very complicated competitive learning, unsupervised learning algorithms to make it work, and he really wanted to stick to the biology as much as possible. So convolutional net basically are a very simplified version of this with this idea of convolution and pooling trained with backpropagation. And this is an example of one of those neural nets kind of having been trained to recognize handwritten digits, and this is to show the robustness of the representation to shifts. So that's the input, that's the first layer, the 6-feature map, the first layer. This is after pooling and subsampling by a factor of 2. So the window over which we do pooling here is 2 by 2, and we step them by 2, so the result is that those maps have half the resolution as the map before. And then again, a bunch of convolutions that combine multiple maps from the previous layer and detect combinations of features. And then pooling again, there's nonlinearities at every stage. And then again, convolutions. And by the time you get to this level, the representation is very distributed and is robust to shifts and distortions. And so you can recognize objects. Not only can you recognize single objects, you can also recognize multiple objects. So this is something we realized pretty early on, that you could apply the convolutional network not just to a single location where you would get one answer, but you could make the entire network convolutional. So all the layers are convolutions. Even what we now call a fully connected layer, you can think of it as a 1-by-1 convolution. And so you get a score for every location, for every category, and then you can sort of post-process that and get the best interpretation. And so that's very crucial because that allowed us to basically recognize multiple objects without doing prior segmentation. At the time, every pattern recognition method required you to separate every object in the input, and with this, you didn't have to. So pretty soon we were able to implement this in a relatively modest hardware. Unfortunately, this is a new computer and the videos don't play, so I have to play them by hand. Let's see. So this is a younger version of myself at the time that Homer and I met. And this is circa 1992 or so. This is my phone number at Bell Labs in Homedale. It doesn't work anymore. And I hit a key, and a video camera captures the image, feeds it to a 386 PC. The 386 processor is older than most of you in the room, and then recognizes all the characters. And we actually run the neural net. We had a special compiler that could compile a neural net trained with our Lisp environment to a very optimized piece of C code that would run on a digital signal processor board. And the DSP chip was actually manufactured by AT&T as well. So this was all in-house technology. This chip was capable of 20 megaflops, which was unbelievable for the time. This is Donnie Henderson, one of the lab engineers, and Rich Howard, the lab director. Donnie is the guy who actually assembled the system, the demo for the system. So that was cool. Pretty soon we realized we could actually build real systems that could have applications. So we got together with a product group at AT&T who was a subsidiary of AT&T called NCR, National Cash Register, and they built large machines to read checks for banks. And we built a check recognition system for them, and it was the first time the system was good enough to be practical. And so they deployed it very widely. It was the first time convolutional nets were deployed, to my knowledge. They were deployed in automatic teller machines, so you could deposit a check and the machine would read the amount on the check automatically. This was around 1995. Mostly deployed in Europe at first, and then the second deployment was in the US with check reading machines, very high volume check reading machines. And at some point in the late 90s, those machines were reading on the order of slightly less than 20% of all the checks in the US. So this was a very successful application of neural nets. Part of the system, the system is pretty much well described in this highly cited paper here from 1998, but the work was all done before that. This was, a few years later we decided to write a long paper about it, but we built the system before. This was very successful, except that the very day we were succeeding, we were celebrating the deployment of that system in banks. AT&T announced that it was breaking itself up, and the research lab stayed with AT&T. The development group went with Lucent Technologies, and the product group went with NCR, and so the whole project was disbanded the very day we celebrated the deployment of the technology. That was a little depressing. So in our lab, we had, it was a small group, less than 10 people or so, and we had people, of course, working on neural nets, but we also had the people who invented kernel machines and supervector machines. So this is a picture of Larry Jackal, who was the head of the group, Vladimir Vapnik, the inventor of supervector machines, or one of the three inventors of supervector machine, really. One of the real inventors is Isabelle Guillon, actually, and Bernard Bozer. And this is Léon Bottou. And back in 1995, Vapnik and Jackal had a bet, and the bet was Jackal bet one fancy dinner that by March 14, 2000, people will understand quantitatively why big neural nets working on large databases are not so bad. Because it was kind of a mystery why neural nets were working so well. There was no real kind of precise theory of why they work so well. Vapnik bets one fancy dinner that Jackal is wrong. But if Vapnik figures out the bounds and conditions, Vapnik still wins the bet. Okay, so this was a thinly veiled incentive by Larry Jekyll to convince Vladimir Vapnik to work on the theory to explain why neural nets work so well. Okay, and there was a second bet. Vapnik bets one fancy dinner that by March 14, 2005, no one in his right mind will use neural nets that are essentially like those used in 1995. Jekyll bets one fancy dinner that Vapnik is wrong. And it's signed by Vapnik, Jekyll, and me. I was a witness. So there was no dinner in 2000, but Larry Jekyll lost that one. We still don't have a good theory for why neural nets work so well. But Larry Jekyll won that one because in 2005 it was the start of the renewal of neural nets, and so people were actually starting to use neural nets more and more. And so Vapnik lost this one. So there was a dinner in 2005, and they shared the bill because each of them lost one half of the bet, and Léon Bottou and I just enjoyed the meal. So since then, convolutional nets have made a lot of progress. I'm sure you've all heard of the ImageNet competition that was won in 2012 by our friends at University of Toronto, Jeff Hinton's group with Alex and Ilya, and Alex Krzyzewski, Ilya Suskever. So they came up with one of the first very efficient implementations of convolutional nets on GPUs that allowed them to train large convolutional nets on large datasets like ImageNet very efficiently. And many of the other teams, like ours, for example, only came up with GPU implementations a few months later and missed the deadline for the ImageNet competition. And what's clear, this is a visualization I borrowed from my friend Rob Fergus, who's at NYU in Facebook, and it describes kind of the type of motifs that are detected by convolutional nets at various layers. And so they attempted to visualize what type of inputs will maximally activate a particular detector at several levels in the system, and came up with this thing where at the low level you get oriented edge detectors, and then a few layers up you get motif like circles and corners and gratings and things like that. And then a few layers up, you get parts of objects, and then a few layers up, you get objects, etc. So the hierarchy in the network reflects the hierarchy of the compositional hierarchy of the visual world. And this is something that's very important. The reason why layered architectures are good is because they sort of capture, they mimic the kind of compositional hierarchy of the natural world, if you want. Complex things are formed by assembling simple things, and those are formed by assembling even simpler things, etc., etc. So over the last few years, there's been a lot of progress in the performance of the system in terms of accuracy, and that was correlated with an increase in the number of layers. So the more layers you add, and the bigger you make the network, the better they work. So over the years, in 2014, there was networks like VGG, which had something like 20 layers. Back in the old days, the convnets we used typically had 7 layers or something like this. And then they started having, 15 layers or so with AlexNet. And the year afterwards, they had 20 layers. And then the year after that, they had, 40 layers. And the year after that, the ResNet, which was proposed by Kaming He, who at the time was at Microsoft Research Asia, who is now at Facebook AI Research in Menlo Park, came up with this idea of ResNet, where he ended up training networks with 152 layers and still be efficient. And it's based on the idea that you can have those connections that skip layers in such a way that if a pair of layers fails, basically that layer becomes transparent and essentially becomes the identity function. And that allows for kind of fail-safe mechanism, and you can have many, many layers and still have it work properly. More recently, Lawrence van der Matten, together with collaborators at Cornell, came up with this DenseNet architecture where basically inside you have blocks where you have those skipping connections, but they skip multiple number of layers inside those blocks. And then you have pooling in between. And if you, and this works really well. So that was one, architectural progress is one way things are progressing. But there's also algorithms and implementations. This is a paper that was very recently published at Facebook of an example of how you can parallelize the training of something like ResNet, the ResNet 50, which has 50 layers, on 256 GPUs, and you can train this entire system in about an hour on 256 GPUs in parallel. This is in multiple machines with fast communication between the machines. And this is a combination of software implementation. This uses the Café2 system, which is being developed at Facebook as an execution engine for neural nets, and algorithm refinements and architectures. So the first ImageNet, AlexNet network trained was taking several weeks to train. Now we can train them in an hour with essentially the same performance. With DenseNet, the performance improvement is not just in accuracy, but also in speed. So DenseNet is a way of basically reducing the size of the network and the amount of computation, but still getting the same performance. In fact, they used something called the multi-scale DenseNet, which has multiple paths in the system, and they can be stopped at any time. So whenever there is a high score category at any type in the process, using kind of this multi-scale approach, you stop, you don't compute the rest. And it's only when an image is ambiguous that you kind of keep computing the layers. And you end up with something like a 2.6 speed up in recognition speed with the same performance for an architecture like compared to an architecture like ResNet. So every day on Facebook, people upload. So there's, as of 2 days ago, there is 2 billion people on Facebook. It just passed 2 billion just a couple days ago. And it's 2 billion average monthly user. So you take an average month, and you have 2 billion people on it. And people upload somewhere between 1 billion and 1.5 billion photos per day on Facebook. Every single one of those photos goes through 4 convolutional nets. One that computes tags, general objects, the category of the image. Is it a landscape or indoor? Is it a wedding or a birthday? Is it a portrait, or is it things like that? Or more specific things, is it a dog of a particular breed? Is it a plant of a particular species? Things like that. There's a few thousand of those tags that are computed. The second neural net detects objectionable content for content filtering. The third neural net does generates a caption for the visually impaired. So if you are blind and you want to use Facebook, you can't see the picture, but Facebook will describe them for you using a convolutional net. And then the last one does face recognition. That one is turned off in certain countries, but it basically automatically tags your friends when you upload a picture of your friends. And it works amazingly well. So face recognition is one of those applications where I didn't think myself convolutional net was good for initially. And when I saw the result, I was amazed. So one of the things we've been working on Facebook is you train a system to recognize objects with many, many categories. And in the end, you get some sort of feature vector, which is kind of generic. It can be used for any kind of task you want. And in particular, what you can do is take a few 100 million images and then compute the nearest neighbor graph of all those images in the space of features. And so for every picture, every photo, you know what the 100 nearest neighbors of this picture are within the collection of 1 billion or 100 million. And it allows you to do funny things like find the shortest path between one image and another. So here is an example. You take this dog and you take this cat and you ask the question within the collection of 100 million images, what is the shortest path in feature space that takes me from one image to the next, to this one continuously. And the dog sort of more or less smoothly turns into kind of a cat-looking dog, and then a dog-looking cat, baby cat, and then a cat. And this is possible because of a library called FAIS. So this means the Facebook AI Similarity Search Library, which is open source, and that you can download, and it's an extremely fast nearest neighbor implementation, essentially, using all kinds of tricks for indexing. So pretty quickly we realized we could use convolutional nets for navigating robots, for robot navigation. So things like applying a convolutional net convolutionally on the image. So it would classify every pixel in the image using its surrounding as to whether this pixel is a traversable area or an obstacle. Okay, so this is a result of applying a convolutional net that says, you can drive here, and these are obstacles you cannot drive through. Same here. Here you can drive, these are obstacles, and the purple thing are the boundary between obstacles and drivable areas. And for objects that are nearby, you can get the data from stereo vision. Stereo will tell you whether something is traversable or not. And so we used a cool trick for this robot, which is that we collected data using by just running the robot around and then collecting labels using stereo, and then use the stereo labels to train the convolutional net. And in fact, we train it in the lab, but then as the robot runs, it trains itself. It continues training itself, and it adapts to the environment. And that worked really well. Let's see. So this is the kind of convolutional net we used. It was applied to sort of bands of images, and it can, so it uses the neural net to kind of label every pixel in the image, and the neural net runs at about 1 frame per second, which is too slow for navigation. It's good for long-range navigation, but too slow for short range. So we have another stereo vision system for short range that runs faster. And then the result is put in a map, and you can use this map to do navigation and to go to a particular point in the world. And in the end, the system can drive itself, relatively efficiently. So this is an example of this robot running around with those annoying students making its life impossible. This is Raya Hatzel. Here on the left, she did a postdoc at CMU, and then she worked at SRI for a few years, and now she is head of the robotics research group at DeepMind in London. The other gentleman is Pierre Samanet, and he also works on robotics at Google. And both of them were quite confident they could jump in front of the robot because they wrote the code. So a couple of years later, we realized we could use this not just for traversability, but for kind of slightly more complex task in particular called semantic segmentation. I'm going to show you a video of this as well. Oops. So this is a work done by Clément Farabet, Camille Coupry, Laurent Najman, and myself. And this consisted in taking street images and training a convolutional net, again applied convolutionally to the whole image, but looking at patches at multiple scales to classify every pixel as to whether it's the road, the sidewalk, a car, a pedestrian, a tree, a building, a door, etc., whatever categories we had. I think this one was trained with 33 different categories. And at the time, it was the best system of its kind. It had the best result on 3 standard data sets for this. It was about 50 times faster than the best runner-up. It's far from perfect. People have gotten much better results since then. But this was, before the deep learning revolution. We're talking 2010 or so, 2009, 2010. We submitted a paper describing the system to CVPR in CVPR 2011. And it was, I was sure it was going to get accepted, and it was rejected. It was rejected because people said, basically, we don't know what a convolutional net is, and because we don't know this method, we don't believe that a method we never heard of could get such good results. That was essentially what they meant. It wasn't said that way, but that's essentially what it meant. So the funny thing is, in 2011, we could not publish a paper at CVPR that talked about convolutional net. Nowadays, you cannot get a paper accepted at CVPR unless you use convolutional nets. So the revolution occurred really, really quickly. So this gave some ideas to a bunch of people working on self-driving cars, in particular at a company in Israel called Mobileye. They were using other techniques until then, and they got a bit of an epiphany using convolutional nets, and they started using convolutional nets in their systems. They eventually sold the license of the system to Tesla, and so the Tesla cars that came out in around 2015 used the Mobileye system. But then Mobileye was not satisfied with the relationship with Tesla, and they divorced. And so the Tesla that came out in 2016 were not actually as good as the one in 2015 because they didn't use that vision system. But now they recovered. Since then, they kind of built better systems. NVIDIA also got very interested in self-driving cars, and in fact started a big project on this. I'm going to show you maybe a video or two on this. Let me start with this one. So this is actually in Homedale, New Jersey, where Homer and I used to work. The building was abandoned for 10 years in Homedale. This was the Bell Labs building. And recently it was, so this is the building you see in the back. That's where Homer and I used to work. And what they have here is a car that is trained by imitation learning. And this is before it's been trained properly, right? So it doesn't drive very well. So basically, the convolutional net just looks at a picture from the camera and then observes the steering angle of the human driver. And then after a few thousand miles of training, it basically can drive itself. This is Urs Müller. He used to be a colleague of ours at Bell Labs. And then he had his own little company, and he collaborated with us on this robot project. And he sold this company to NVIDIA about 2 years ago. And now he's head of one of the groups at NVIDIA that works on self-driving cars. And this video is about a year and a half old, and already the system could drive itself pretty well. Not entirely reliably, but pretty well, including on dirt roads and things like that. Yeah, stick their hands out. And they had a demo at CES. I think this is a demo video that NVIDIA put together for CES last year. So this system uses a combination of Urs Müller's self-driving capability using imitation learning and some other systems built by other groups within NVIDIA to do explicit detection of objects and things like this. But it drives itself pretty well. Okay, so there are quite a lot of companies working on self-driving cars, and I know there are research projects in Taiwan also on self-driving cars. It's a very interesting area at the moment, very hot. Facebook is not working on this, although we're working on this a bit at NYU. In fact, we're looking for postdocs to work on self-driving cars at NYU. If anybody is graduating from a PhD, wants to do a postdoc in New York, working with these guys and with us at NYU on self-driving cars, please apply. If you're watching by Facebook Live, you're welcome to apply too. Okay, so more recently we worked on. When I say we, I shouldn't say we because this is not work I'm involved in. I'm merely the director of the lab. This is work done by people at Facebook AI Research. This is called the Deep Mask. So this was a system that would, a convolutional net that would not just produce a category for each object, but also a mask of the object being recognized. So here would be the elephant in the center of the picture. And out of this idea was built a complete system to kind of recognize and locate and outline objects. So this was built a couple of years ago. And this is some of the results where all the persons are detected and outlined, and including the frisbee, the person, even the blurry people, the broccolis. This is the American idea of a Chinese dish. And I don't particularly like broccoli, so now we can have a robot that picks out the broccoli out of the... we can also count sheeps. Okay, but that was a year and a half ago. Since then, we made some progress. So a few months ago, Kai-Ming He, the same of ResNet fame, and Georgia Gokchari, Piotr Dolar, and Urs Gershik came up with this architecture called Mask RCNN, which is sort of a very simple, conceptually simple architecture that combines the idea of RCNN and deep mask. And it's very much just a convolutional net, except at the output there is a network that can look at sort of windows of various sizes and make a decision as to what the object is and also generate a mask. And the performance of the system is, in my opinion, nothing short of amazing. So it beats a number of standard benchmarks on the COCO dataset, and it outlines every person. So this doesn't do semantic segmentation. This does what's called instance segmentation, which means that it's not just one blob that you can identify as person. You actually outline every single person here, separating them from each other. And the baseball bats too. And wine glasses and TV and etc. And sheeps, again, you can count sheeps. You can still count sheeps. Cars is, I think, 200 categories. And this system, the same system, can actually identify key points on human bodies, 17 key points, and for that, reconstruct the pose of the bodies. So that's an example of result here. Other examples. And this is just one system, does all of that. In fact, there is another system being developed at Facebook in Paris, at Fair Paris, by Yasunas Kokinos and other people that actually improved on the pose estimation system using basically a differentiable graphical model on top of mask RCNN, essentially, to get slightly better, slightly more accurate pose estimation. So the amazing thing with mask RCNN is that it runs at 30 frames per second on a single GPU, and it runs at 5 frames per second on a mobile phone, just in software on a mobile phone, and using all kinds of tricks. Unfortunately, I can't show you the video of this, but it's pretty amazing. At Facebook AI Research, we publish all of the work we do, and we also distribute a lot of code in open source. So if you go to github.com/Facebook Research, you'll see a long list of different projects. There's a bunch of projects that are not under this category. For example, Torch and PyTorch are different. They are outside because they are projects that Facebook kind of drives but doesn't own, if you want. Facebook is just one of the participants. And there's, PyTorch is the main deep learning research environment that we use these days. And it's very convenient. It's got a Python front end and efficient back end. We have, of course, the Dark Forest Go engine, which is open sourced. FastText, which is a very fast text classifier and text representation learning system. It's all C++. FairSec is a neural machine translation system that uses convolutional nets instead of recurrent nets, written in Torch. FICE, which I already mentioned. ResNext is a kind of a new version of ResNet, if you want, with parallel path, implemented in Torch. DeepMask is all open source. And ComAI and Parley are kind of experimental platforms to test dialogue systems and learning based on dialogue and communication. And then there is Torchcraft. We have a big project at Facebook to build a bot that can play StarCraft. StarCraft is a real-time strategy game, for those of you who don't know. Every one of you below 30 probably knows what I'm talking about. And it's a very challenging task, probably more challenging than playing Go, and very interesting, and nothing works at the moment. So, okay, so let me switch gear and talk about the real obstacles to AI, which I think is what we need to clear to make real progress in the future. So we need machines that can learn to understand how the world works and understand how the world works the way we do. And we learn how the world works by just observing it. We observe what happens. We know what's possible. We know what's impossible. We learn the effect of our actions, the consequences of our actions by acting in the world. And as a result, we learn to perceive. We learn to maintain a updated estimate of the state of the world. We learn to reason and plan. And the combination of perception, predictive models, memory, reasoning, and planning is what constitutes intelligence and common sense. And a crucial part of it is prediction. I'll come back to that. So common sense is something that people in AI have been chasing for a very long time and not really being able to kind of circumscribe it. So it's the mass of knowledge that all of us rely on when we act in the world or when we talk to each other. When you talk to someone, you assume that person knows a lot about the world. You don't realize it, but we need to have a lot of background knowledge about the world to be able to communicate. So here is a very simple example that is a very classical example in classical AI. A sentence like this one: the trophy doesn't fit in the suitcase because it's too large, or the trophy doesn't fit in the suitcase because it's too small. So in the first case, the it refers to the trophy. In the second case, the it refers to the suitcase. And you can lift the ambiguity as to which word the pronoun refers to because you know how the world works. You know what a trophy and a suitcase are supposed to do to each other. One is supposed to contain the other. But if you don't know that, if you are a dumb computer, you have no way of resolving this ambiguity about what object the pronoun refers to. If I say a very simple sentence like this one, which has 9 words in it, it's very short. Tom picked up his bag and left the room. You don't have to know anything about Tom or the room or the bag. You can imagine the situation where Tom probably is sitting at a table, probably has to stand up and extend his arm and pick up his bag, then walk towards the door and open the door and get out of the room. And you know he's not going to attract magically his bag by telekinesis. You know he's not going to fly through the room. He's not going to disappear like this guy here. He's not going to go right through the wall. He's going to have to open the door. So there's a lot of things like this that you know are impossible because you never observed them. And you just learn that by observation, just living in the world. And so there is this question of how do we do this? How, babies learn very basic things about the world after a few months of life. So for example, the idea that there is an object, and if I put the object behind another one, you know it's still there, right? That's called object permanence. Babies learn this, after a few months of life, maybe at 5 months or so. The idea that if an object is not supported, it's going to fall. You learn this between the age of 6 months and 8 months. So this kind of basic notions of intuitive physics, you have to learn them, and it takes a while. And we'd like machines to be able to do this. And we don't know how to do it. And that's, I think, in my opinion, the main challenge that we have to solve for the next few years. So common sense, perhaps, is the ability to fill in the blanks, predict the future from the past, infer the state of the world from partial information, infer past events from the present state of the world, filling in the visual field at the retinal blind spot. We do this all the time. We don't even notice we have a blind spot in the retina, but we don't realize we're blind at that location. Anything that amounts to filling in the blanks. And the idea that we can train machines to predict what the missing information is what I call predictive learning. It's really a form of unsupervised learning. There are many arguments for why unsupervised learning is necessary. This is one by Jeff Hinton, who says, unsupervised learning is the only way that we can collect enough constraints, enough data to constrain all the parameters of a very large machine, right? So his argument, which is a little simplified, but is basically there. The brain has about 10 to the 14 synapses. We live for about 10 to the 9 seconds. So we have a lot more parameters than data. This motivates the idea that we must do a lot of unsupervised learning, since the perceptual input is the only place where we can get 10 to the 5 dimensions of constraints per second. So we have to basically learn to predict everything we perceive. And to some extent, you could say that the prediction is the essence of intelligence. So that led me to this slightly obnoxious analogy, particularly if you are someone working in reinforcement learning, but I'll make it up, I promise. The fact that if you measure the amount of information that you ask a machine to predict in different modes of learning, reinforcement learning, supervised learning, unsupervised learning, in reinforcement learning, you're asking the machine to predict a single scalar once in a while. How well the machine is doing, basically. That's all you ask the machine to predict. To predict. Well, that's all the information you give it once it tries to predict. You're only telling it whether it did good or bad, and that's only one piece of information. Supervised learning, you're telling the machine the correct answer, but the correct answer is usually a very weak piece of information. It's only a few bits, right? It's one category among 1,000, let's say. The reason why ConvNets work well on ImageNet is not because ImageNet is so large, it's because there are so many categories. If you train a convolutional net with the same amount of data just to do pedestrian detection, the features you'll get would be terrible because there's only 2 categories. You're not giving enough information to the system at every step. So what that means is that you're going to need a lot more samples to train a reinforcement learning system than if you train a supervised learning system, which is why AlphaGo has to play more Go games than all of humanity in the last 3,000 years to be able to play well. Or the Atari players have to play millions of games before they get good. They get good, but they have to play millions of times. So this doesn't quite work in the real world. Unsupervised learning or predictive learning, you get millions of bits per sample, but those are weak bits in the sense that it's not an unambiguous category like you get with unsupervised learning. You're asking the system what's going to happen next. And of course, a lot of different things could happen next. So that leads to this analogy that if you measure in terms of amount of information you ask the machine to predict and you give it at every time, you give a lot of information in the context of unsupervised learning, you get a little bit of information in supervised learning and very, very little information in reinforcement learning. And so if intelligence is a cake, the bulk of the cake is unsupervised learning, the icing on the cake is supervised learning, the cherry on the cake is reinforcement learning. And that upsets some of the reinforcement learning people. But I'm not against reinforcement learning. You have to notice that this is a Black Forest cake, and Black Forest cake have cherry all around inside. And the cherry on top is not optional. It's required. So we do quite a lot of reinforcement learning at Facebook. This is work by Yann LeCun, who actually won one of the tracks in the Wisdom competition last year. And this is using relatively, a few tricks, but relatively standard reinforcement learning. There is, another work by people at Facebook AI Research in New York and Paris of playing StarCraft, and they're making a lot of progress with this, but it's still very far from having a complete bot. But we have to go back to the root of reinforcement learning and look at an old paper by Rich Sutton, who is the grandfather of reinforcement learning. And he had this quote, which is very interesting. He was proposing an architecture called DINA, which is an integrated architecture for learning, planning, and reacting. He says the main idea of DINA is the old common sense idea that planning is trying things in your head using an internal model of the world. This suggests the existence of a more primitive process for trying things not in your head, but through direct interaction with the world. Reinforcement learning is the name we use for this more primitive, direct kind of trying. And DINA is the extension of reinforcement learning to include a learned world model. So basically, it's this idea that you have a world model that the agent acts upon. And the agent acts on the world, but internally it has a world model. And so it can try things in its head before it actually acts in the world. It is very useful if the world is a dangerous place. So for example, people who work on self-driving cars have a big problem these days because they'd like the cars to train themselves by using reinforcement learning. The problem is that the car will not learn that running into a tree is dangerous unless it tries to run into a tree. And you can't afford to destroy 4 million cars to train the self-driving system. As humans, we don't need to run into a tree to predict that something bad is going to happen if we drive into the tree, or if we drive on the left side and we run into a car coming the other way. That's because we have a model of the world that predicts this for us, right? And so we need machines to have models of the world like that. So how does that work? In fact, it's very classical optimal control. In classical optimal control, the way you plan a trajectory is that you have a model of the world called a plant simulator in optimal control. And this model of the world, from the state of the world at time t, predict the state of the world at time t+1, given the command that you give it. And the state of the world goes into an objective function that you might want to minimize. So you run your system, your simulated system, for a number of steps. and you find by gradient descent, basically by backprop to time, the sequence of commands that will optimize the objective function you want to minimize. Let's say the amount of energy you spend for a rocket to reach the space station or something like that. This is a very standard technique that NASA was using in the 60s to plan trajectories for rockets. It's very classical. And so that leads to kind of a question of how do you build an intelligent system. So an intelligent system, this box here, inside has an agent that tries to optimize an objective function that measures how happy or unhappy it is. It gets an idea of the state of the world through a perception module. So that's an estimate of the state of the world. And then it generates actions on the world, and the world responds with percepts. But inside the agent, you'd like the agent to have some sort of model of the world that it can use to try things in its head before actually trying it in the world. So inside the agent, there is an actor that produces action proposals that go into the world simulator that produces predicted percepts. And the actor also has a critic, which is a module that predicts the long-term value of this objective. And so if this guy is a self-driving car, and this guy is a simulator of the car, and it knows there is a tree in front of it, it can try to drive through the tree and then predict what's going to happen. And this guy is going to tell it, even before it crashes into the tree, this is not good. Your objective here is going to be really crappy after a while. So all of those modules are trainable. We know how to train this one. We know how to train that one. This one is just trained by predicting future value of this guy. This guy is just trained by optimizing trajectories and then training it to predict them. The question is, how do we train this? So in the end, if we had all those modules that are trained, here is an initial perception. We can run the world simulator multiple steps. The actor runs multiple steps, and the critic every time, and we can sort of figure out a sequence of action coming out of the actor that minimizes the overall cost coming out of the critic. But how do we train a world simulator? And that's really the main problem, I think, the main obstacle that we need to solve. And I'll tell you in a minute why it's complicated. So a couple of years ago, a group at Facebook, Adam Lehrer, Sam Gross, and Rob Fergus, built a system a convolutional net, basically, to predict intuitive physics. So you have a stack of blocks, and the system is trained to predict what the state of the blocks is going to be after a while. So it predicts things like this, where this is a couple blocks on top of each other. This is what actually happens when you observe. This is the real world. This is a simulator. And this is what the neural net predicts is going to happen. Pretty good prediction. Except if the stack is a little too tall, it's very hard to predict exactly where those blocks are going to be. And so you get those fuzzy predictions because the network cannot predict exactly where those things are going to be, so it makes a fuzzy prediction. So how do you solve this problem of fuzzy prediction? Well, that's one question. There's another question which I'm going to skip because I'm running out of time. So this is about recurrent neural nets that deal with textual inputs and try to predict the state of the world from textual inputs. But I'm going to have to skip this. So one reason we want to do prediction is estimate the state of the world. So if I say Mary went to the hallway, you have in your head a representation of the hallway containing Mary and Mary being in the hallway. And John moved to the bathroom, Mary traveled to the kitchen, she's not in the hallway anymore. And so if you have a neural net that can sort of maintain a current state of the world, you can probably do some inference. And this is what all those slides I skipped are doing. It's called the entity net or entity ARNN. And it's one of the first systems. It's actually the first system to solve all 20 of the Babi tasks, if you know what this is. But the point I want to make with this is a slide I stole from Jason Weston, who is working on dialogue at Facebook. If you have a dialogue of this type, Mary went to the hallway, John went to the bathroom, Mary traveled to the kitchen, where's Mary? The real answer, so here's the answer of the system. It says the playground. And then you say, no, that's incorrect. If the system can predict this is what I'm going to say next, that means it knows its answer was wrong. Where is John, the bathroom? Yeah, that's right. So if you can predict this, then prediction is kind of an essential piece of being able to conduct a dialogue. In fact, Jason and his collaborators did some experiment like this on a data set called Wiki Movies. using data from Mechanical Turk. So these are kind of dialogues. Who wrote the Linguini incident? Richard Shepard. Richard Shepard is one of the right answers here. Blah, blah, blah. So these are kind of dialogue that can educate the machine actually as to what the correct answers are. And in fact, what he shows is that by using a state predictor system based on memory networks, he actually gets better performance faster with fewer training trials than if you use sort of pure black box optimization methods or kind of more reinforcement learning type methods. So prediction speeds up learning. The ability to train a model of the world speeds up learning. But that really asks the general question of unsupervised learning. What is unsupervised learning really? It's the ability to capture dependencies between variables. So here you have two variables, and these are points that you observe, and there's obviously a dependency between those two variables. You could capture this dependency using some sort of contrast function that takes low values on the points, on the data points, and higher values outside of the data points. And those two contrast functions are equivalent as far as this is concerned. And what you'd like is to come up with some sort of learning algorithm that carves this contrast function, let's call it an energy function, so that it gives low energy to points that actually occur in the data, and higher energies to points that don't occur. And it's easy enough to shape a function in such a way that it takes low values at points that you know, but it's very hard to give it higher values at points that you don't show it. And so I made a list of 7 different methods to do so, but all of those methods, although very interesting for their own sake, are kind of out of date now that we have something called adversarial training. So I'm going to have a very simple hand-wavy explanation of what adversarial training is, and I'm sure many of you are aware. I mean, I know there's a lot of people working on adversarial training here in Taipei. So basically, you want to train a system, for example, to predict future video frames, right? So X is the past video frames, and Y bar is possible prediction of the future. So for example, I'm going to put a pen on the table, and then I'm going to lift my finger and ask the machine, what is the world going to look like half a second afterwards? And perhaps the machine will predict this point, which corresponds to the pen folding to the left and to the back. But in fact, if I wait and I look at what the world produces, the world answers with this point. Both points belong to kind of you could call this a manifold of possible plausible futures. And what you'd like is a cost function. When you train this generator, you'd like a cost function that does not punish the generator for producing a point that's on the manifold, even if it's wrong. You only want to punish it if it produces a point that's outside the manifold. Okay? So what you'd like is a cost function that tells you how far from the manifold you are. And the problem is, of course, you don't know this manifold. So that function that tells you whether you're on the manifold or not has to be trainable as well, has to be trained. And that's basically the idea of adversarial training. You have 2 neural nets, a generator that produces predictions, and a discriminator that tells whether those predictions look good or not. So you can think of this as, this is the network I want to train, and this is a trainable objective function, a trainable cost function, basically. Or you can view it the other way around. You can think of this as a density model, a contrast function of the type I was talking about earlier. And you can think of it just as a smart way of generating points outside of the distribution of data. Okay, so the discriminator is going to be trained with 2 types of points. Points coming from the actual data set. This is the actual frame that appears after the sequence. And you're going to train the discriminator to produce a small value on the outside. So basically, the surface here is what's computed by the discriminator, where Y is the input. And for every actual data point, those blue beads, it's going to try to make the value of the function as low as possible. So dig a hole in the function at that location. And then it's going to look at points produced by the generator, and it's going to assume they are wrong and basically make the output of this discriminator function as high as it can. So it's going to take those green points and make them as high as possible. Simultaneously, this guy is going to train itself to produce points that this discriminator cannot tell are fake or real. And this guy can cheat because it knows the gradient of the output of this guy with respect to its input. So it knows in which way to modify itself so that next time it generates an image, this guy won't be able to tell the difference with the real data. Okay? And the result is that this guy trains itself, it has a source of random numbers, and it trains itself to produce Y with the same distribution as the actual real data. And this guy trains itself to discriminate between real and fake, but in the end, it can't. So in the end, you get this kind of picture where you get good predictions that look really much like the real world, are not exactly identical, but they look very much like it. And the discriminator trained itself as a contrast function like that. So there is many, many forms of adversarial training. One of the most popular ones in recent months is the so-called WGAN, or Wasserstein-GAN. This was proposed by Martin Ajovsky, who is a PhD student at NYU, and Léon Bottou, who is a research scientist at Facebook in New York. In fact, Martin works with Léon. And they've gotten really good results with their method. This is actually an old form of GAN called DC GAN that generates pictures of bedrooms. So it trains basically what amounts to a reverse convolutional net. You put random numbers in, you get a bedroom picture out, or you can get manga characters, or you can get faces, and you can do arithmetics on faces. So you take the vector that is at the input of the network, and you have it generate faces like this. So you can figure out what input vector will generate this, what Z vector, the random vector, will generate this face. And you take the vector for this face, subtract the vector for this face, add the vector for that face, and then generate an image, and you get the vector for that face. So man with glasses minus man without glasses plus woman without glasses equals woman with glasses, which is kind of amazing. And there is all kinds of examples of this running around. I'm going to skip this. This is another type of GAN called energy-based GANs, which my student Jake Zhao and others developed. And this is when it's trained on ImageNet, and it captures kind of local dependencies of images, but not really sort of the global structure. So if you're in the back of the room, it looks nice, but in the front of the room, you can't tell what object these are. They're not real objects. This is if you train on dogs. You get soft dogs. And one problem with GANs is that you can't train them to generate text because they're really not designed for discrete data. So Jake Zhao, again, and some of our colleagues at Harvard came up with this idea that we could use an autoencoder to autoencode, for example, text or images, and then regularize the code of the autoencoder using adversarial training. So basically, there is a generator and a discriminator, and the discriminator tries to discriminate between data produced by the generator and data coming out of the encoder. But both the generator and the encoder are trained with a gradient from the discriminator. So the encoder generates data that is as close as possible to the distribution produced by the generator, and the generator trains itself to produce a distribution that's as close as possible to the encoder. But at the same time, the decoder needs to be able to reconstruct, so this guy can't lose too much information. Once the whole system is trained, you can put a random vector here, run to the generator, and run the result to the decoder, and what you get is a generative model of text, for example, or MNIST digits. So these are reconstructions of the autoencoder. These are generated samples by picking a random Z vector and then generating a sample. And this is interpolation in Z space. So you take a particular character, and then you linearly interpolate the code in code space, and you generate samples, and you can continuously transform a character into another. There is one here, between all the characters on the line. And you can do this for text. So this is a text generated by a random vector, so it doesn't mean anything. A man is on the corner in a sport area, or a man in a cave is used an escalator. It's not even grammatically correct. And then you have another vector that generates another sentence, and you can linearly interpolate between them, and you basically continuously change one sentence into another with this process. You can also do fun things. So you have a sentence like this: a man in a tie is sleeping and clapping on balloons, whatever that means. Then you take the average vector of sleeping, subtract it from the vector that represents this sentence, and then add the average vector of all the sentences that contain walking. and then you generate a new sentence with this. And basically it substitutes sleeping for walking, but then it kind of makes sense, right? A man in a tie is clapping and walking dogs. Sort of makes sense. Okay. Perhaps more relevant to models of the world is video prediction. So you show a few frames to a convolutional net and you ask it to predict what's going to happen next in the world and generate the next video frames. And this is what happens if you use least square as a criterion. So you try to train the convolutional net to produce an image using just a least square training. You get a blurry prediction because it's impossible to exactly predict what's going to happen. But if you use a combination of adversarial training and a few other tricks, you get these kind of predictions that are sharper and kind of make sense. So the predictions are indicated by the red border. This is kind of the same system applied to videos shot inside of apartments in New York. And so as the camera moves, rotates, the system has to predict what the apartment looks like. So for example, here you have bookcases, and as soon as the border turns red, those bookcases you see are fake. They are invented by the network, essentially. The side of this couch here is invented by the network. So it has kind of captured a lot of regularities about how what apartments are supposed to look like by kind of being able to propagate those things. But it's probably a better idea to do this kind of prediction in kind of a more abstract space like semantic segmentation. So this is work by Pauline Luc, Natalia Neverova, and Camille Coupry. And I skipped the title slide here. Jakob Verbeek and myself. And they are Facebook AI Research in Paris. Jakob Verbeek is at INRIA. And these are examples where you train the machine, you take a bunch of frames from a video of a street, and you run a semantic segmentation engine on it, frame by frame. It's been pre-trained. And you train the system to predict the next frame of semantic segmentation without necessarily looking at the raw input. And it predicts that if a car starts turning to the left, it's going to continue turning to the left. If a pedestrian starts crossing the street, it's going to continue crossing the street. And the scenery is going to keep moving because the car is moving forward. That this car is going to keep pulling in front of the other car, etc. It's very useful to be able to predict this kind of stuff if you are trying to build a self-driving car system. Okay, I'm probably way over time. Yeah, about 10 minutes. I'm just going to flash a couple results of what's called style transfer. It's not really the kind of style transfer you've heard. This is work by a team of Facebook AI Research in Tel Aviv, in Israel. And they used a fairly complicated architecture, which I'm not going to go into the details of, that basically allow to do style transfer from a photo to a very kind of a small icon, if you want. And they applied this to some of the people in our lab. So this is me in a few years ago, and that's the avatar that's generated for me. And it can make me cry or be surprised or be happy. This is Lior Wolf, who is one of the members of the lab in Tel Aviv, Yaniv Tagman, and Adam Poliak. And this is kind of the 2D version, and now they're working on the 3D version that generates 3D avatars from pictures of people. Okay, I'm going to end with a slightly kind of philosophical, a couple of philosophical slides. So the first thing is, clearly deep learning and neural nets are inspired by nature to some extent, but they're not copied on nature. We cannot copy nature because if we copy blindly, we don't understand what principles make nature work. And the picture I'm showing here is a picture of a kind of an airplane that was built by this guy Clément Ader in France in the late 19th century. It was steam powered, and this plane, or a predecessor of it, actually took off on its own power. But very few people probably here knows about it. This was 13 years before the Wright brothers. I mean, 6 years before the Wright brothers, but his airplane actually took off quite a long time before the Wright brothers. And he's been forgotten outside of France because his airplane was not controllable. And so he copied nature, he copied his plane on the design of a bat, but really sort of didn't think about control and stability and things like that. So that's an example of the danger of sticking too close to nature without actually trying to understand the underlying principles. And we can reflect sort of a little more philosophically about the fact that, of course, we know that science drives technology, but it's also the case that technology drives science. So, a lot of new sciences are born from the study of technological artifacts. So, for example, the telescope was invented very empirically, but that kind of explaining how it worked resulted in classical optics. Newton worked on this a lot. The steam engine motivated the research around thermodynamics, the Carnot cycle and all that. This is because of steam engine, and this is how entropy came about. The fact that there is a quantity that you have to take into account to model the cycle of a steam engine. This is the basis of all modern science, and it came out of an artifact, of an invention. The invention of the airplanes caused people to work really seriously on aerodynamics and understand, thrust and lift and drag and things like this. Mechanical and electromechanical and electronic calculators led to computer science, which is now a science, but wasn't until fairly recently. And telecommunication led to, telephone and radio communication led to information theory, which again is a basis for a lot of different things we do, a basic methodology and science, mathematics, and theorems. So one question I have is, what is the equivalent of thermodynamics for intelligence? Is there an underlying principle for intelligence, kind of like the basic laws of thermodynamics, that we can apply to intelligent machines, and which is common to every intelligent machine, whether it's artificial or natural? And if I have a scientific program in my life, that's probably trying to kind of discover this. What are the underlying principles behind artificial and natural intelligence? And of course, the best way to do this is to build machines that are as intelligent as we can build them. So I've spoken too long. Thank you very much for your attention, and I'll be happy to answer questions.
Okay, we have time for a couple of questions. Okay, go ahead. You can use the microphone on your table.
Okay, thank you for the wonderful talk. And I want to ask a question that you say to conquer the challenge in learning, basically we need machines to understand more about the real world. And in our human brain, we actually understand a lot about the real world, and we call them domain knowledge or whatever that is. And I want to ask about your opinion about how we can encode those human knowledge possibly in our brain into something machine more understandable to facilitate them to conquer the learning tasks. Thank you.
So I don't think we as engineers can encode that knowledge. This was the program of classical AI in the 1980s, of trying to compile human knowledge into a set of rules that we could write down. But we can't. We don't know how to do this. It turns out to be very, very complicated. We can't even do it for vision, right? So if there is something very humble that deep learning has taught us, is that stochastic gradient descent running on the GPU is better at designing vision systems than any engineer in the world, okay? That's very humbling if you're an engineer. I am an engineer. So, and the other humbling statement is the fact that we have a very hard time sort of consciously inspect to kind of reduce our thinking process to a set of a program. That's classical computer science and programming you're describing, right? So the machine will have to derive this knowledge by itself by looking at the world, and that's the basic principle, the idea why you want to use machine learning, right? And the machine will have to come up with its own representation of the world, and that's the crucially complicated part of machine learning that deep learning kind of attempts at solving. Not completely, unfortunately.
Okay, Go ahead.
I have a kind of specific question about the energy-based model. I know you connect energy-based model with GAN and consider the discriminator as the energy function. But my question is, in the original theory of GAN, in the end, the discriminator will be useless. It's flat all over the place. So it do not really reflect the energy of the data. And I know you replace the discriminator by using an autoencoder, but I do not understand why when we replace it by the autoencoder, it becomes an energy function. Can you have more explain on that? Thank you very much.
Right. So I had a bit of an animation there, and it's not entirely clear theoretically what the story is, in a sense that. So the little animation I had is one where. Let me see. This is one where you start with an energy function computed by the discriminator, which may be flat, for example. So it doesn't discriminate between real and unreal, between real and fake. And because the green points are bad initially, they push up the energy where they are, and so eventually the energy function kind of looks like this. Now, so this is sort of an intuitive picture, but it's not entirely clear that the energy function will take that shape. But it is a stable state. Now, if all the green points are near the manifold, it could be that this function will be completely flat and will still be a stable state. So there are stable states that are not good solutions. And there are stable states that are good solutions, and the question is, how do you get there? So that's one of the mysteries of GANs, which is that it's not very well understood that all solutions to the optimization problems are not good. Only certain ones are good, and the ones that are obtained by the training process seem to be okay, but not all of them. So I think there's a lot of theoretical work to do around GANs. I think it's probably easier to do in the context of energy-based GANs rather than the probabilistic form, but I may be wrong. The Wasserstein GAN approach, I think, is very promising. So it says, you basically, the basic idea of Wasserstein GAN is that you limit the derivative of the discriminator by basically limiting the size of the weights inside the discriminator, and therefore this function has a limited slope. And so when you put the green points outside of the manifold of data, the function can go to infinity, and that's what makes it work. So that's one way of limiting it. In energy-based GAN, we just design the energy function so that the thing cannot go to infinity. But so, I think a lot of those questions are just not understood. It's a bit like neural nets in the late 80s, where people would try neural nets and it wouldn't work because they didn't quite understand all the tricks. And there was no real theory to tell them what to do. And I think with GAN, we're in the same situation. Sometimes it works, sometimes it doesn't, and we don't know why. That makes it interesting.
Yeah, go ahead, Homer.
Mentioned many times. Projection, and I have a non-technical question here, and that is, how do you predict 20 years from now AI will be? Okay, and we can have. No, I'm expecting a free dinner. Okay.
All right. Yeah. So, traditionally in technology, people overestimate short-term progress and underestimate long-term progress. So, generally, we think that once we figure out the principle behind something, we can just build it, and eventually it will happen. But we figured the principle behind rockets a long time ago in China. But there is a big step between figuring out the principle and actually building rockets to go to the moon, right? It's considerably more complicated. So we generally underestimate the complexity of bringing something to practice in the short term. But then we also underestimate long-term progress because it's difficult to foresee revolutions. So there are revolutions in computing, for example. I mean, who would have thought in the 40s that we would have, computers of this power for this price and this size? I mean, it's amazing. And And so I think we're in the same situation in AI. You know, people in AI have been making optimistic prediction in the 60s and 70s, and now they've become extremely prudent and careful about not making wild prediction. At least people in academia, people in startup companies who are looking for investment, you know, still make kind of wild promises. But so there's probably going to be a bit of a backlash when some of the promises that were made are not going to be fulfilled. But you know, the second half of my talk is basically all about what we cannot do yet, right? With some ideas about how we can solve it, but they're not ready-made solutions. They are attempts at, you know, climbing this hill, this mountain that we're seeing of unsupervised learning. Now, here is the thing: that my picture of AI is that, you know, we have this big hill that we need to climb, which is unsupervised learning or predictive learning, call it what you want. We don't know how many hills, how many mountains there are behind the first one that we will need to climb. It could be the last one, or there could be 50 more, and we don't really know. So that's why I can't tell where we're going to be in 20 years. But you know, I hope we'll have intelligent virtual assistants that we can talk to without being frustrated. We might have, you know, domestic robots that actually work. We'll certainly have self-driving cars, that almost certain. And we'll have much better, you know, medical image analysis systems. I mean, it's going to transform society. There is no question about it. But before we have truly intelligent machines, it's going to take a while.
Yeah. The last question. Okay. We are going to take a group photo, including everybody. So you will find yourself from the Facebook. Yeah. Go ahead.
Okay. So. A human question that it takes a while, actually more than a few years, for human to learn so many things from the real world. So I just wondering that how can we that machine to be trained based on a selected data from the real world, so that the machine can be active just like a human being. Basically, how can we that machine become sense by selected data?
Right. So I mean, the question, of course, is what data should be used for the machine. So there is passive data about the world in enormous quantities on the world. I take all the videos on Facebook or YouTube. It's, you know, millions and millions of hours. So you know, everything you need to know about intuitive physics or how the world works probably is somewhere on YouTube or Facebook. So in that sense, I don't think we are missing any data, but that's passive data where the agent, the intelligent agent, cannot act, right? So then the question is, how much data does the machine need to be trained where it can actually have an influence in the world? And does it have to be the real world? So does the machine have to be a robot? Or can it be a simulated world? And will the skills that the machine will learn in the simulated world be transferable to the real world? So people who work on self-driving cars are very interested in this. A lot of companies want to train their self-driving system on simulators and then transfer the skills to the real world. You know, it's not clear. There's no clear way of doing this really at the moment, but that's a very interesting question. So now, what I'm after is, I mean, people and certainly animals, like let's say cats, learn astonishingly fast. You know, cats learn incredibly complicated motor controls in just a few months. It's with just a few trials, basically. It's amazing how fast they learn. And baby humans learn to speak. You know, learn everything there is to learn about the world in a very short time. In, you know, basically a few hours a day of practice. So how does that happen? There is an algorithm out there that works, that does this. How do we get a machine to do the same thing? Of course, in the short term, we're not going to solve that problem. We're going to cheat. We're going to do like supervised learning, or we're going to use simulators, or we're going to do like AlphaGo. We're going to let the machine, you know, use more training samples than whole of humanity for the last 3,000 years. It's possible in certain virtual environments. It's not possible in the real world, which is why all the success of reinforcement learning are in games, because games you can run very, very quickly on multiple machines, and you can generate millions of examples this way. But there's no similar success for example, robot grasping or locomotion or obstacle avoidance, because you cannot run. That's one big problem with the real world, is that you cannot run the real world fast in real time. It's sad, right? I mean, to some extent, it's actually a good thing.
Okay. Yeah. So let's thank Dr. LeCun for the
Thank you
very
very much.
inspiring talk. Yeah.
好，我们大家来拍个那个大合照。那我们大家尽可能的话，就往中间这个区块集中。那可以吗？对，就是对，往中间靠。如果要入境的话，就往中间集中，因为我们中间才有办法入境。啊。